This video is going to walk us through two complete solutions and then some other problems for using this stoichiometry map properly and identifying your givens and requireds and identifying your root. And then hopefully after that you will be fully confident in using this version of the map that has all your steps written in, and then you simply have to do the steps. And then I'd like you to move on to the other student guide that does not have the steps written in. You can use the one first that has the little symbols to remind you, balance, look for your givens and requireds, recall what you know, and then use the one that doesn't even have those right in your steps. And again, you really want to be solid on using this stoichiometry map. We're going to use it in the remainder of the course in the next 2 units. It only gets more complicated and there's another step coming. So please practice, actually write out your steps, because if you write step 1, balance equation, you're going to remember if you've done that a few times, and then you won't forget that step, which would mess up everything and result in great confusion. So please practice that way. So the first problem we're going to look at is this one. We're going to look at some of the terminology that gets used in the written problems as well. So you might need a bigger screen to make sure that you can see this, but I'll read it out to you as well. So the first one is, how many grams of hydrogen are needed to react completely with 50 grams of nitrogen? So again, this wording, react completely, it just means figure out your balanced chemical equation. If you're given so many grams of hydrogen, how many grams of nitrogen are going to react with it in the balanced ratio? So that's all it means. You can just ignore the react completely after you've read it and just pull out your given and your required. All right, so take a look at that. What is our given and our required? Our first step, checking out that equation. And the question is it balanced as it's given to you? And the answer, very quickly you see, is no. So step 1, get the balancing done in there. Step 2, figure out your given and required. So for this problem, they have given you 50 grams of nitrogen. So that's your given. What's your required? Well, they want to know how many grams of hydrogen. So we're looking at our nitrogen and our hydrogen. And for step A, we're just ignoring the ammonia. We don't even need to think about it. We just need to figure out the two quantities, the two particles that the question is asking about. So we've got that, our nitrogen and our hydrogen. Step 3, recall known values, right? Because it's not in here. There's no molar mass given. Avogadro's number isn't given. So we need to figure out our molar mass. If this was simply written and you didn't have the equation at all, you would be expected to remember that both hydrogen and nitrogen are the Hofbrinkels. They come as diatomic molecules. So you would need to have 2 times the mass of the nitrogen atom for the molar mass of nitrogen, and 2 times the mass of the hydrogen atom for the molar mass of hydrogen. And we always want to remember that we know Avogadro's number. You don't always have to write it out, but I'd put a little NA as the reminder that you know that number. All right, so we are ready to solve this problem. We are starting from a given mass. We've got our 50 grams. Oh, sorry, that's not what I want to do. I want to just use the orange to say we're starting from the mass. We always have to go this way, then we have to go this way, and then where do we want to get to? Well, in this case, they are requiring the mass. This is a mass-to-mass problem, and I'll use the black so you can read it a little bit better. So we've got our 50 grams of our nitrogen. We need to convert to the moles, so we're going to divide by the molar mass of 28 grams per mole. Okay, and if you have this printed off, that can remind you of all of your equations, right? So we've got moles is mass, which we pull from there, divided by the molar mass is going to give us our moles. All right, so divide by the 28 grams, we're going to get 1.8 moles. And this is our given, so this is of N2. We can write a little reminder in there if we're not working on the map. You might want to write a little reminder of what species it is. So it's just the N2. Now we need to convert through our molar ratio. So back to our balanced chemical equation, we have 3 hydrogens for every 1 nitrogen. So it is 1.8 times 3, and then just divided by 1, so that does nothing. We are going to get 5.4 moles. And again, keep track of what you're doing. So you could write right under here what the required is. So bracket in that this is hydrogen, bracket in that's all nitrogen, whatever works for you. We're working with hydrogen at this point. And now where do we need to go? Well, follow our little map. We are going up to mass. That's what the equation asked for. So we need to multiply by the molar mass of our required in this case. So 2.02 grams per mole. We're going to multiply 5.4 times 2.2, and we're going to end up with 10.8 grams. And again, this is hydrogen. So you'll want to do a little therefore statement. So therefore, 50 grams of N2 reacts with 10.8 grams of hydrogen. All right, and that is the end of that problem. Now, if you remember, just give you a minute to take a look at that. Okay, and you can pause when you come to this point in the video if you need to. So back to our problem. It had a part B, and we just ignored part B until we were done part A. So part B asks how many grams of ammonium are produced in the above reaction. So we're going to use that same given value of 50 grams. So in this case, our balanced chemical equation stays the same. The given of 50 grams of nitrogen and its molar mass that we can recall stay the same. The only thing that's changed is what they are requiring. So in this case, we've got the same balanced chemical equation, so we're done. We've got the same given in its molar mass. We are now requiring the mass of ammonium. So now we're comparing nitrogen and ammonium and ignoring hydrogen. So this is quite handy. And if you will notice, I've erased it, but you're basically just redoing the same thing. So I'm going to walk you through the same steps, but if you're doing this, you could notice before you've erased your steps that you've already done part of it. So you don't really have to redo it, but you might want to rewrite it for step B without doing the equation. So we know we've got 50 grams. We already solved for our moles. We already know this is 1.8 moles. So we've gotten that far. We know that information from doing part A. We don't have to redo it, but we do have to pay attention once we get to this heart of our problem solving because we've changed our required. That means we've changed our molar ratio. All right, so now we are needing to find ammonium. So it is 2 NH3s. All right, we're starting from nitrogen to every 1 nitrogen. So now it is 1.8 times 2 divided by 1, and we're going to end up with 3.6, oops, that's not a 6, 3.6 moles of our required, which is the NH3. And again, they want the mass back, so we're going up here. All right, so we are going to take that same route again, going this way, going this way, going this way. All right, so we need to use the molar mass, though, of ammonium this time. So we are going to multiply by the 17 grams per mole. That's the molar mass of ammonia, 3.6 times 17, and we're going to end up with 61.2 grams of NH3. And again, do your therefore statement because it shows that you know what you started with and what you finished with. And you can identify that 61.2 is in grams and then it applies to ammonia. So you want your therefore statements to include all that information. So that's how we solve that part A and part B. That's how we extract the information given from those problems. All right, so let's take a look at another problem. And again, if you're feeling confident, you're like, I can follow through all this, you can stop this video and just go and solve problems. But if you want to see the walkthrough, then stick with me. Make sure everything is erased. All right, so next problem. This has 4 parts. We're going to solve A, and we're simply going to look at B, C, and D. All right, so part A says, propane can undergo the following combustion reaction to form carbon dioxide and water. And it's given us the combustion reaction, and you don't need to wonder if we're going to be tricky. We're not. If there are no numbers out front indicating the number of particles, then check if it's balanced or not, because that might not be stated whether it's a balanced or unbalanced equation. If you don't see any of those coefficients out front, then wonder if it's balanced and check. But if you do see coefficients, we're not going to be tricky and put the wrong ones. So if you see coefficients, the equation is balanced. All right, and for this part of the course, we are just going to ignore that they're gas, liquid, solid. It doesn't matter at this point. It will matter later. So if 3 molecules of propane is combusted, all right, so we've got 3 molecules of that is combusted. That means it's reacting with oxygen. How many molecules of CO2 are formed? So that's part A. So again, we've got to do all of our steps. So step 1, we already have our balanced chemical equation. You want to pull that out of the equation. You want to write it out so that you've got it separate from all the words. All right, and then take a look at your given. We've been given 3 molecules of propane, and we have required is our molecules of CO2. So what have we got? Do we need our molar mass of the given? We can figure it out, but if we take a look, we're going from molecules to molecules. We're never going to need the mass root, so we don't need our molar masses. But you might want to just put this in as a reminder that you can figure that out if you need it in parts B, C, or D. So that could be information that you can get, but don't waste your time if the question doesn't need it. So it doesn't need you to figure out the molar mass. Don't do it. We will need Avogadro's number because we're working in molecules and particles. All right, so let's get going and solve that part A. All right, so we have 3 molecules of our given. Okay, and let's identify our root. We can go from moles. We need to go through the heart of it and get back to particles. All right, so 3 molecules. I'm not going to write out the whole number, but to get from molecules to moles, divide by Avogadro's number, and we're going to get 5 times 10 to the negative 24 moles. Again, that's not negative moles, but we're only working with 3 molecules. So it is a very, 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 very small part of the mole, being 6.02 times 10 to the 23. Okay, so it's not negative particles. We can't have negative particles. All right, so let's convert through our molar ratio. Oops, I got myself there. Put it back. All right, times 3 CO2s to every 1 propane. All right, so take our number of moles times 3 divided by 1, and we're going to get 1.5 times 10 to the negative 23 moles now of our required CO2. And then let's get back to particles since that's what they want. We're going to multiply this time by Avogadro's number, and we're going to get 9 molecules of CO2. And we are done. You can do your therefore statement. Therefore, 3 molecules of propane will react with with oxygen to produce 9 molecules of CO2. Now, if you are feeling really confident in your stoichiometry and in your understanding of what all these numbers really mean in the balanced chemical equation, you will notice there is a shortcut, all right, for this particular problem. You can go molecules, stop by to do the multiplication by the balanced ratio there, and then get to particles without using Avogadro's number. So this is a shortcut. You can go particles to particles using that. However, it is critical, absolutely critical, that you understand there is no shortcut up here. Okay, you can't go, just make that look like there we go. You can't go this way. That's not a shortcut because masses cannot equate. So one particle can react with 5 particles. One particle of propane reacts with 5 particles of oxygen. So you can convert through that balanced ratio doing particles. You can convert through the balanced ratio doing moles because it's the same idea, particles and moles. It's a 1-to-1 ratio or whatever it is. But you can't get from mass to mass because the masses of the particles are different. So you cannot convert here. That's not a shortcut. All right, so we've completed that particles to particles problem. We're going to go back and take a look at the rest of the problems that were in there and just take a look at pulling out our given and our required. All right, so part B was how many molecules of oxygen gas were needed to react with 3 molecules of propane. And I'm just going to show you identifying different givens and different requireds from the same balanced equation. All right, so the same balanced equation that we are given. But for B, they've given us propane and they're requiring oxygen, and we ignore both of the products. And we just write down our given values, our required values. We'd write down the known values for them if we needed them, and Avogadro's number, and carry on, follow our route. C has 16 molecules of water are formed during the reaction. So they've given us water. How many molecules of propane were reacted? So our required is propane. So we've got the given of water, we've got our required of propane. Follow through your route. And again, it is molecules to molecules or particles to particles. All right, and then D, how many molecules of oxygen are needed? So our required is oxygen to react with 3.01 times 10 to the 21 molecules of propane. All right, so they have given us a value for propane. So this is just how you identify your given and required. And for any problem, there's only 2 things you're looking at. One given, one required, and no matter how complicated the balanced chemical equation is and how many different types of particles and molecules and elements are in it, you're only ever paying attention to 2 to solve a problem and just ignoring the rest. Pay attention to 2, pay attention to the coefficients out front to get your balanced ratio in order to convert moles to moles, or if you wish, particles to particles, and that's all you need to do. So that's taking a look at that one and solving a particle to particle problem. The last thing we are going to look at, again, without going through all the steps, because I think we are familiar with them now, is just pulling out some terminology. All right, so here's another example. So in this problem, we have a 2-step problem, and again, just do A. You'd read over B to have an idea of where you're going for B, so you maybe don't erase work you've done in A that you could reuse, but by and large, just ignore B to start with. So A, how many grams of silver chloride are produced from 5 grams of silver nitrate that reacts with an excess of barium chloride? So again, we just want to look at the terminology. When it says an excess, all it means is you have more than enough barium chloride to fully react with the 5 grams of silver nitrate you've been given, because there's a specific ratio of the silver nitrate to the barium chloride. If you didn't have enough barium chloride to react with the silver nitrate, then not all 5 grams of particles would react, right? Because they react in a particular ratio. You need enough of each. So they want to know precisely how much of the silver chloride is going to be produced from 5 grams of silver nitrate, given that you've got plenty of the barium chloride to make that 5 grams fully react. All right, so then you want to pull out your, just need a little bit of sticky. Okay, you want to pull out your steps there. So this is for part A. So for part A, we've got our balanced chemical equation. Again, I had to take a look and put in the numbers that I needed to balance it. They've given us 5 grams of silver nitrate. They want to know how many grams of silver chloride, so that's our required. And then the fact that it's reacting with excess barium chloride, we can just ignore. We have enough to fully react what we've been given, and that's all we needed to know. We now ignore barium chloride and we ignore barium nitrate and just focus on the 2 that they've given us. Pull out your molar masses, remind yourself you've got Avogadro's number, and then you just identify your root and carry on solving. And again, this is a mass-to-mass problem, so you're just going to take this root, go this way, head back. Make sure you pay attention to your silver nitrate and silver chloride and put your molar ratio in there the right way around, required on top and given on the bottom so it cancels out, and carry on and solve that problem. All right, so that would be for part A, and just understanding that terminology of excess. Let's take a look at part B. All right, so for part B, how much barium chloride is needed to completely use up the silver nitrate? So they told us we had an excess up here. Now they want to know precisely how much barium chloride is going to be reacted with the silver nitrate. So we might want to know how much barium chloride we'll have left over if we dump too much in. All right, so we have the same balanced equation that we had the first time, so we won't need to rewrite that. I'm just pointing out how you can do these. So you would want to notice same balanced equation, so you wouldn't necessarily rewrite that. I wouldn't. You want to change your givens for step 2. So we've still got the same given of silver nitrate in this case. You want to pay attention. Has our given changed? No, it hasn't. What's our required? Now we want to figure out the mass of barium chloride. So we need a different required molar mass. So figure out your molar mass of barium chloride. We don't need to re-figure out the molar mass of silver nitrate. We've got that from part A. I wouldn't even rewrite it. I would just use it again. All right, and now we've got to just solve mass to mass again. So your root is the same, but what changes? All right, so if our root is the same, we're going a mass to mass root. This part all remains the same, because we're starting with the same given value and the same given species in the balanced reaction. But this changes, right? So we need a new molar ratio for our barium chloride to our silver nitrate. The molar mass changes in order to convert back to the mass. So those are the 2 things you need to change, but you do not need to redo your work converting mass to moles for part B. You just say, see part A, we've got this many moles of silver nitrate. Now I'm going to convert 2 moles of barium chloride and back to the mass of barium chloride. And you're done. And that's how you read some of that terminology in the questions, so that you can just understand it and then put it aside and then simply pull out the nice clear information that you need to work with. I hope that helps. Please let me know if you've got any questions. Please make sure that you start by working with the guide that looks like this, that has your steps to solve, and that you then move on to the guide that is blank and you write in your steps. Do that for several problems, and then if you want to move on after that to not having the guide at all, but I would still be clear about your steps. I should still see step 1, step 2, step 3 done, even if you don't write a step, just 1, 2, 3, 4, 5, 6, all done really clearly, however you want. I would stick almost with writing this map out by steps, maybe not circles, but by steps on your page. But how you solve it after that is up to you, as long as I can clearly see your steps, I can clearly follow along. I know that you're solving for oxygen, for example, instead of nitrogen, that you are very clear in what you're doing. All right, have fun.